Okay, sounds good. So when you need time for oh no, you'll have that. So we believe they are.
Yeah. Hope so.
More traditional American styles. Have a timer on. Yes, you will have your money. Probably, I think it's a good time to get going. All 4 minutes.
So time like the president. Looks weird.
Right?
Yeah. Oh, I didn't do it.
We could come to.
Yeah.
Yes. Maybe. This. Spend a lot, yeah, free. Yeah, we also try to. From biology and from the energy sector, very challenged and then.
And 3 times. Answer that. Yeah. Oh, that's very good. Yeah. Good. Thank you. Yeah. Good job.
Over every student here, actually, everything more about yeah. Here, let's set a mic here.
Oh, I have to compare.
Oh, which is very beautiful. So I like it. Is it like?
So,
It is much more easy. Still actually a lot of years of learning large changes in life. In current German don't is Germans here don't bring their publishing patterns. That's true. Was treated very in the age yes, really really over from my country to other like ticketing that's or Germans are very old men. Yeah, it's just me. And then he was sort of was not with that my but it's like sort of like yes, and you have a lot of really basic needs and with our experience like giving to message to move away from so relying on that and becoming a lot overall. So yeah. Well, I guess if you buy them sort of usually don't have natural gas today, don't have the like with more the whole comparative. He's hanging the one the right to be filming the renewables like you're like the one total 1 second. It was one told and said how many things that we find out we didn't use having and you know you want to get this email and you okay. Because you know, sometimes it really affects and that's really one of the energy from a GDP. So you keep it very much sort of the agreements to something from least right now with the changes of the partnership. I mean, like it's just a shows because I'm not going to necessarily with that. That good from the one Germany, they have something history. So, when I'm in Friday, you are imagining 6,000 out, you were right, you see, yeah, it's all done. What you know, that's right. Yeah, oh, okay, yes, you very good. You know, you share and I share it all. You're not, I'm saying, which part of your life should be there? So right now we're these yeah. How would you ask you what's doing and maybe
Yeah.
That is true. That is true. My tendency is to super. Really? I see that it is. Where it doesn't do. Do you think okay, good move. Sorry. Good work. Hopefully, my name is Emily, one of the two co-chairs. We run this year, it's engaged for us. I come from Rensselaer Polytechnic Institute. I'm right now department head for industrial system engineering, but especially mechanical, aerospace, and nuclear engineering. That's where my degree was, and actually I stayed in Boston at IT for 7 years for my PhD, and that was 20 years. It's a long time. So hopefully a little bit my own brief just to get you started. I'm really privileged and feel very grateful that today we have our plenary talk for this session from Dr. Robert Kleinberg, and is involved in both of those two centers that we highly respect, Columbia Center on Global Energy Policy and Boston University Impact Management and Allocation. So without further ado, Robert, the floor is yours.
Well, thank you, Emily. Real pleasure to be here. I'm actually surprised there are so many people in the room. This is like the last morning, 8:30 in the morning. I was expecting like maybe 3 people, but so this is a very gratifying turnout. I am Robert Kleinberg. My topic for today is problems with greenhouse gas life cycle analyses of U.S. liquefied natural gas exports and locally produced coal. This has been a very technical symposium for those of you who have been here the 3 days. This talk is a little bit different because what I'm particularly interested in after a career in geophysics is the intersection between technology and policy. And that's what you're going to be seeing in this talk. So it's going to be pretty heavily how that intersection sometimes hits, often misses. And it's our responsibility as technically informed people, the people who really understand what's going on, to sort of make sure the policymakers don't wander too far away from facts and reality. Sometimes it's hard. Okay, let's get started. This sort of the story sort of starts out last fall with a article in the New Yorker magazine. I subscribe to the New Yorker. It is not my usual go-to source for information about energy technology or atmospheric chemistry, but they did they did happen to have an article that was relevant to these fields back in October. The title was "A Smoking Gun for Biden's Big Climate Decision." And the title, "A New Analysis Suggests that Liquefied Natural Gas Exports May Well Be Worse for the Environment Than Burning Coal." The author was Bill McKibben, a well-known environmental activist. And so looking at this title, I wondered, okay, what's Biden's big climate decision and what's the smoking gun? So the big climate decision revolves around what is known as a public interest determination, mandated by the Natural Gas Act of 1938. I'm going to quote from the act. No person shall export any natural gas from the United States to a foreign country without first having secured an order of the Commission authorizing it to do so. The Commission shall issue such order upon application unless it finds the proposed exportation will not be consistent with the public interest. Now, back in 1938, public interest sort of revolved around the price and availability of natural gas. But as with many acts of Congress and laws in the United States, it has been repurposed for current concerns, particularly in the Obama and Biden administrations, where public interest was expanded to include climate change concerns. So the big question that those administrations asked the Department of Energy to look at was does exporting of U.S. natural gas to other countries increase or decrease greenhouse gas emissions and therefore make climate change not as bad or worse? So that is the big question now that the Department of Energy has to answer. And on January 26th, partly due to that article in the New Yorker magazine, the Department of Energy announced that it was updating its public interest analysis and pausing permitting of all facilities allowed to export LNG while this update is underway. This sort of, I guess it made it into the newspaper like one day, but it really did rock the industry for reasons that you will soon see. Okay, so the big climate decision. Now, just to put things in perspective, natural gas liquefied, put into tankers and shipped around the world has rapidly become a major U.S. export. Now, back in 2016, basically we weren't exporting any liquefied natural gas at all. But in the intervening years, we have become, in the last 8 years, we have become the world's largest exporter of liquefied natural gas, as shown by this chart. So the United States is sort of darker, looks like it was black. There we go. Here's this black line starting 2016, going up at present to almost 14 billion cubic feet a day, which is like 14% of all US production. So it's a big part of US production, and it outmatches every other country, many of whom have been in the business for a long time. Now, I just want to point out there's a few glitches here. There's a big dip during COVID when energy markets were all upset. Okay. And then the other big change was since Russia invaded Ukraine and gas was cut off from Russia to Europe. Europe is the world's largest importer of natural gas. Russia was the world's largest exporter of gas. It was kind of a monopsony situation, which basically got blown up as a result of the war in Ukraine. And the US, with its gigantic capacity, was able to come in and basically save the Europeans from, from freezing during the winter. So for which they were grateful, and from which we made a lot of money. Win-win on that one. So this is a big business. Okay, so what does this pause really mean? Well, anything that is currently exporting can continue to export. They already have their permits, no problem. There's a lot of stuff being built now on the Gulf Coast in the United States with permits that have already been granted. They're not going to be taken away. But the projects that are sort of at risk here by this permitting pause, it's 11 projects totaling 25 billion cubic feet of natural gas per day. That would like triple the exports of almost triple the exports of the United States. I guess increased by 2.5 times. So it's a really big deal in international commerce. It affects every country in the world that imports gas. And these 11 projects account for, wait for it, $100 billion of capital expenditure in Louisiana and Texas. So you can bet that the congressmen from Louisiana and Texas are looking at this very, very carefully because $100 billion is real money, real big money. So this is a big climate decision. On the other side, you have the environmental issue of, okay, how much greenhouse gas are we putting into the atmosphere? Way too much. Is this going to make things better or worse? Okay, so I need to go through some background to understand the rest of the talk. And that is how greenhouse gas emissions are assessed and measured. So I'm just going to, this is a pretty simple slide. I'll try to go through it efficiently. So masses of various greenhouse gases are added together to produce a composite emission effect. The two big greenhouse gases, particularly in gas train, are carbon dioxide, which is, of course, the product of combustion. We all know that. And methane, which is the primary constituent of natural gas, which is a very powerful greenhouse gas. Much more powerful than carbon dioxide, but emitted in much lower quantities. So you just can't add these masses together to get a climate effect. We all understand that. So that's because these gases differ in their radiative efficiency. In other words, their effectiveness as greenhouse gases can't simply add the masses together. So back in 1990, this multiplier called the global warming potential was devised by the Intergovernmental Panel on Climate Change for the purpose of allowing various gases to be added together. Carbon dioxide was assigned a multiplier of 1. And then everything else is a multiple of that. So if you have emitted masses of carbon dioxide, a mass carbon dioxide, and mass methane, there's a little equation at the bottom which shows you how to add them up. So what's called the carbon dioxide equivalent, maybe you've heard of this, carbon dioxide equivalent math, is the mass of carbon dioxide you get for a given policy choice, plus the mass of methane times the global warming potential multiplier for methane. So this is basically this CO2 equivalent method that is universally used in analyses of this type. Universally used. In fact, there's been 4 papers in 2024 using this methodology to assess the climate change effect of liquefied natural gas. Big deal. Okay. These global warming potential multipliers are kind of, well, kind of fuzzy. You get a choice of time horizons, which you can choose depending on how you're feeling. It's rather arbitrary. I wrote a 50-page treatise. That was my COVID year project on global warming potential. Be happy to share that with you. But basically, the 2 usual choices for methane are a 20-year horizon and a 100-year horizon. You'll see how that comes in a minute. Okay, so let's get to the heart of the matter. So on the left is a 2-part chart, and I'm just going to describe each part individually. First, on the left, this is an analysis done by the National Energy Technology Laboratory, which is a division of the U.S. Department of Energy, so kind of official U.S. government estimate. And there are 2 bars, one for coal, that's domestic coal produced in China and burned in Chinese electric power plants. Okay. The other bar is LNG, that's liquefied natural gas, produced in the United States, shipped to China, and burned in gas-burning power plants in China, in Shanghai. So, and these bars have 3 different colors. The black part of the bar is CO2 from power plant operations. In other words, you've got your fossil fuel, you're burning the fossil fuel, you're making electricity, how much CO2 comes out? That's pretty easy. It's kind of, you look that up in handbooks and so on. And we all know that when you burn coal, you get, kind of like more than twice as much carbon dioxide per unit of electrical energy that you get out than if you burn gas. So carbon dioxide, so coal has a big disadvantage in the global warming game, right? We're all trying to get rid of coal. The green part of the bar is the carbon dioxide that's emitted in the supply chain. So, for example, you can see that the green bar on the LNG side is bigger. That's because it takes into account things like, okay, you've got to put this liquefied natural gas in a tanker, ship it all the way from New Orleans to Shanghai. Wow. So there's a lot of greenhouse gas produced as a result of that shipping. And there's also the liquefaction part, which takes energy and therefore emits carbon dioxide and so on. So that's the green part. And there's only a little bit on the Chinese side because you load the coal into a train, ship it to Shanghai. Trains are pretty efficient, doesn't give off much CO2 per megajoule of electrical energy that you get out from the plant. The red part of the bar is methane. That is mostly comes from leaks and other incidents on the what we call upstream, which is the gas wells in the United States, the gathering gas pipelines in the United States, the processing plants, the liquefaction plant, and so on. A certain amount of natural gas escapes, right? On the order of a few percent. And so that's the red part of the bar. And you can see that the METL analysis that was done in 2019, no question, US natural gas, much better than Chinese coal. Let's ship as much natural gas to the Chinese as possible. Ask them not to burn so much coal. That's going to be better for the environment. So this passes the public interest test. Hooray. Okay. And everybody's happy about that. Okay, then along comes Professor Robert Holworth from Cornell University. And sort of in a series of preprints that changed from month to month, last year and last fall and then this spring, and picked up by the New Yorker magazine, he came up with a very different assessment. So let's look at that. Again, the vertical axis on the right side is, yes, again, the grams of CO2 equivalent. That's the combination of methane and carbon dioxide. But now it's not per megajoule of energy at the electrical energy at the output of the power plant. It's the thermal energy at the input of the power plant. And so that's why these bars look very sort of different sizes. You'd think they'd be more or less the same, but they're not. So Howarth is using a different energy denominator in his greenhouse gas intensity measurement, vertical axis. So, but again, looking at the bars, again, for the black part, that's the power plant emissions. Coal, much worse than liquefied natural gas. Fine, we all agree. But his estimates for the supply chain greenhouse gas emissions are much different. So there's the green part, which is the CO2, but what's really different is the red part, which is methane. Howarth's methane contribution to greenhouse gas emissions much bigger. That's why I spent so much time telling you about how to add up these things to make a bar chart. Okay, so I looked at this, big controversies, Department of Energy flustered. Do we need to reassess? Who's right? Article in the New Yorker magazine. So I decided, okay, let's just go through these papers and look in detail about how they differ because they're describing exactly the same situations. Why are the results so different? So, so the main things that are different are, first of all, current methane emissions, NETL estimated 1.2%, upstream leakage, Howarth estimated 4.6%. I and a few other people in this room look at this data a lot, and I think most people would say, oh, it's kind of in between. Okay. But NETL sort of with a low estimate, Howarth with a higher estimate. Global warming potential. I told you, you can make a choice. What's your multiplier? That's for you to decide. NETL selected 36 as their preferred multiplier, and Howarth selected 82 as his preferred multiplier. Okay, that's the GWP method for you. You get to put in the number you want. What about future methane emissions? Well, in 2019, nobody was talking about any changes in the future. But in the last year, there has been tremendous regulatory and legislative activity, both in the United States and Europe, to limit methane emissions. And so now, I mean, the US Congress apparently estimates that we can reduce our methane emissions in the US by 90%. Yeah, that would be nice. But anyway, somebody thinks we can. So it seems like we should at least consider what might be happening in the future as a result of these things that are now in law. You know, sometimes the laws don't work, but okay. There's the energy denominator in the greenhouse gas intensity. I told you there were two different choices. You could either use in the denominator here, dividing the carbon dioxide equivalent, you could divide electrical energy output in megajoules or thermal energy input in megajoules. Very different answer. And I'm not going to go into detail about how different it is. I do refer you to my preprint in SSRN number 49-15-327. Memorize that number. That has all the details for how these things differ. Overall effect, NETL systematically, every time it had a choice, chose parameters that favored gas. Howarth, every time he had a choice, made the choice that favored coal. Well, maybe that's why these bars are so different. So, who's right? Well, the thing is that when these analyses were done, nobody actually asked climate scientists. I mean, these analyses were done by energy analysts, smart people, our friends. Some of those in the audience know Harvard Ravi Kumar, Debbie Gordon, people like that are very respectable. They all use this global warming potential with the CO2 equivalents, but the climate scientists say that method is misleading. So I have a large number of quotes in the preprint, again, referring you to the SSR preprint. I just picked out one representative. This is from Jan Fuglesvik, who's a very well-known, respected climate scientist, published in GRL 2000. There is no single scaling factor that can convert between CO2 and CH4 emissions. The application of GWPs does not give equivalence, and hence the concept of CO2 equivalence is misleading. As the GWP concept is currently formulated and applied, it is associated with significant shortcomings. And their literature, climate science literature, is rife with these comments like this. So, if we're not going to use CO2 equivalent on those bar charts that I showed you that were used by both NETL and Howarth, then what should we use? Well, let's look at the Paris Agreement. Fundamental measure of climate change adopted by the Paris Agreement is, quote, the increase in global average temperature. That's right up top of the Paris Agreement, Article 2, Part 1A. So 2015. So let's do that. So what I did was I went to the Intergovernmental Panel on Climate Change documentation, a fifth assessment report, has analytical equations for calculating the increase of global average temperature using real physics model, incorporating the multi-exponential decay of carbon dioxide in the atmosphere, thermal lags in the earth, and so on. So it's pretty, I mean, the equations are basically pretty simple. I could do it without a computer, but pretty comprehensive and has physics in it, unlike the global warming potential, which is kind of a back of the envelope, estimate where you get to pick your, multipliers. So if you look at, so what I did was I modeled 1,000 terawatt hour per year electric power industry, which is like the size of the Indian power industry. I assumed that it ran for 50 years. The horizontal axis is years. And so the first 50 years, either it burns all coal or all natural gas, take your pick. If it burns coal, you get this steady increase in temperature as the carbon dioxide in the atmosphere builds up and up and up. Once you turn off the industry after 50 years, which is a typical infrastructure lifetime, the carbon dioxide does not go away. Carbon dioxide is kind of like a forever chemical in the atmosphere. And so it very, very slowly dissolves into the ocean, and the temperature goes down very, very slowly over a period of centuries. So let's look at the natural gas version of this industry. Start with the lowest curve. That's labeled gas no leaks. So this is burning natural gas, which produces carbon dioxide. And if there's no leaks, the carbon dioxide that's being emitted, which is much lower than if you burn coal, is shown by the red line at the bottom. Right. If you have leaks, then you've got methane contributing to the problem. And those are all the other colors that are further up. And from 1 to 5% leaks. And that's sort of the realistic range. And you can see that methane contributes a lot to the prompt warming. But once you turn off the power plants and go to your windmills or photoelectric panels, whatever, then the methane goes away pretty quickly because its atmospheric lifetime is not centuries. Its atmospheric lifetime is 12 years. Decay constant. So after a few decades, it's gone. And your problem is gone. And all you've got left is the carbon dioxide produced by that from burning the gas, which is much lower than coal. So this is a very, very different picture than those bar charts I showed you. It leads to very different decisions. Now, I'm not here to tell you what choice to make. That's not my job. I'm here to tell you we need to use the best analytical methods to make these decisions, not some back of the envelope global warming potential where you get to choose your parameters. So conclusion, NETL and Howard are both wrong. And what we should be using is physics-based climate models, just like the climate scientists do. So just to wrap up, recommendations for future life cycle analyses. First one, stop using global warming potential and CO2 equivalent methodology. Problems of global warming potential and CO2 equivalent methodology are well known in the climate science community, and elimination of this unphysical and misleading method is long past due. Second, use the best analytical tools available, general circulation models, meticulously curated by climate scientists. Given the environmental and economic risks at stake, it makes no sense to assess policy alternatives using naive back-of-the-envelope metrics like GWP. The importance of the legally mandated public interest determination fully justifies the use of rigorous models, followed by formal integrated assessment modeling. And finally, let's think about the role of renewable and decarbonized energy sources. Neither of these analyses had any thought about, well, what's the effect on wind and solar and other renewable and low carbon energy sources. The Department of Energy needs to determine whether exported LNG will displace coal or whether it will displace renewable sources of energy in potential markets. They have not done that. So with that, thank you very much. Looking forward to your questions and discussion during the session or perhaps afterwards if you wish. My email address is shown in red here. And so please don't hesitate to get in touch with me if you have further questions. Okay, thank you.
I'm engaged with the research costs, but between Howard's and the other analysis and the
NECL.
are they comparing light with light, since one was using 100-year horizon, the other 20-year horizon, so it's possible to interpret that one is saying coal is better in the short term, the other is saying the same for the long term. Is it possible to tweak the interpretation of that? Or?
Yeah. that's a weakness of this global warming method, that you get to choose. Now, the 100-year GWP was basically sort of originally selected by the IPCC and was adopted by the United States government and is the United States government standard. So every US government report that you see that uses global warming potential uses the 100-year, right? That's the international standard. Okay. Howarth has a long discussion about, well, okay, what should we be using? And he has arguments that are, somewhat convincing, and a lot of people were convinced by it, that the 20-year was more appropriate because, the next 20 years takes us almost to 2050, and people are talking about, okay, we have to limit global warming to 1.5 degrees by 2050. So let's focus on 2050. That points you toward using the 20-year GWP.
I think that the GWP 20 has a higher value than 100 based on half-life, higher concentration. Is that at least something that is reasonable for them, or the are choosing power ratio a lower value than the 36?
Right. Well, there's an equation for GWP, which I did not present. So it's an integration of radiative warmth and so on. And so if you say 20, the equation tells you what number to use. Okay, so you choose your time horizon and turn the crank, and you get a number. You don't get to choose anything you want, but you do get to choose any time scale you want. And you can see just from the real calculation that for the first, and this has nothing to do with GWP, this is just a calculation. But, in the first 20 years, basically, the methane effect is very important. Methane has 100 times the effect of carbon dioxide in the first 20 years. It doesn't take into account the fact that methane disappears quickly after that. So that's kind of a reason why people might take GWP 20, but they're both wrong.
Thank you so much.
Yeah.
Okay.
Thank you. Quick question about this lab. Analytic equations that you model the increased standard structure obviously seem much better to like kind of arguing. And someone who's now thought about this uncertainty was right is that physics is still extremely complicated with the whole like like what would the error bar be right this
Yeah, just the other day I was talking to a climate science scientist actually, and I said, hey, let's work together and show how much superior your methods are to GWP. And he said, okay, but first I want to put in the effect of wildfires, which has feedback effects with global warming and contributes to global warming and so on. And I'm thinking, oh my gosh, there is a lot to consider. So, I mean, what climate scientists do in practice is they have a lot of scenarios. They calculate for all possible scenarios, or there's a large range of them, and then give you a band of possible results. I mean, the nice thing about these equations is that you only get one result from the equations, and these equations are not bad. But you're right. I mean, and that's the reason why policymakers just hate real calculations, because real calculations are complicated, require thought, and actually require understanding plots like this. And you'd be surprised how resistant they are. They just want a number. And I'm not making it up. I mean, I talk to people who work in the White House. Please just give me the number. No, no, no. Nature is not like that. And I think it's our responsibility as scientists and engineers to make sure the policymakers understand that just getting a number is not enough, does not actually point you toward reality. Yeah, it's complicated, yes.
you so much. Great, also, it's my case, learned a lot of life, and I see that since and you're mostly all people, a lot of people on this experience database that are used. They all use the global warming and potential strategies to treat those people who provide this databases. I guess that would be the next big step, to get the better numbers into issues that you want to use using.
Yeah, it's really funny because the energy analysts and the climate scientists and the life cycle analysis people are like three different silos, and they actually don't talk to each other. So I think the life cycle analyses that I have seen all rely on global warming potential methodology because it's a simple input for them, right? And they're not climate scientists. So I think they absolutely need to be educated as to what the complexities are. And so they can make better life cycle analyses because they are really good on the life cycle analysis side, but then their input data, not so good and, garbage in, garbage out. So there's a lot of education to be done here in all three communities. Yeah.
Um, I get the pleasure, yes.
Okay.
See,
Okay.
already consider like supply chains or the presentation, and also, for example, power plants and coal plants were having different efficiencies when they actually go from thermal energy to the electricity. Did you already consider all these things? I know it's a
Yeah.
extra.
Yeah. Yeah. Excellent question. Um, okay. First, with respect to the efficiency of power plants, um, that is explicitly in this comparison. So the reason why um, Howard's choice of energy denominator favors coal is the difference in efficiencies in power plants. Coal power plants are less efficient than gas power plants, so you get a let's see, smaller denominator, which amplifies the effect of coal. I'm sorry, amplifies the effect of gas, and it's explained in the paper. Um, so yeah, that's taken into account here. Um, this is sort of a more holistic global view. There's no energy denominator here, so I don't have to worry about it, and didn't worry about it. This just gives you the equations tell you for various amounts of emission in this 1,000 terawatt hour per year industry that these are the temperatures you get. So this is in many ways simpler because it doesn't have a lot of those complexities of things like power plant efficiency.
Thank you so much.
Yeah.
Okay, can we have round of applause?
How to get rid of this? Oh, I see.
He can.
Okay, why don't you take care?
Yeah.
Yeah, thanks.
You're my turn.